Let's talk about electromagnetism, which is kind of the big concept of this unit, which is how electricity and magnetism are related. So you may remember or may have heard mention of the electromagnetic field. Light is waves in the electromagnetic field. And this is because the electric and the magnetic fields are the same field. And this field, like I've said, is called the electromagnetic field. It's one substance, one concept, one kind of phenomenon. And so electric charge and magnets, those field lines we drew, you can think about that as bending or warping or shaping the field. And they both shape the same field. If there's a charge, it'll act on a magnet if it's moving. If there's a magnet, it'll act on a charge. And this is because in some ways they bend this field in perpendicular directions, but it's still the same field. So a magnet, for simplification, a magnet might bend it up, down, but the electric field bends it left, right. Now it's not really like that because it's a three-dimensional shape and it's complicated, but what you can think about, what I really want you to have just as a seed in your brain for if you go on in physics or just kind of to have a seed to think about the world, is this means that electricity and magnetism, they're the same thing, just viewed from different perspectives. So kind of like you hear the phrase like two sides of the same coin, the electromagnetic field is the coin, and electricity is, if you look at it from one angle or from one side, so to speak, you see everything as electricity. You can see certain phenomena, certain things moving as electric phenomena. If you look at it from a different angle, that same stuff that's happening can be explained using magnets and dipoles and stuff like that. Now, how do you look at it from those different angles? That's where you get into more advanced physics and some not terribly messy, but more than we want to get into here, math. But they're the same thing, just which idea are you looking at? And this is going to be hard to wrap your brain around. It's not something I'm expecting you to completely understand or I'm going to test you on. It's just something to set the seed and plant this seed so that if you go on in physics, you kind of have this already in mind. So how do we kind of take advantage of that fact or how these are connected? Well, the one way is we can create these things called electromagnets. So like I said, electricity and magnetism, just two sides of the same coin. And this means magnetic fields can be created by moving charges. So if I move a charge, not only does it create an electric field by existing, but by moving, it creates a magnetic field. So we can create that's not how I'm going to talk about electromagnets. Just so it flows better in the notes. It's still true that moving charges create magnetic fields, but we're going to talk about a device called an electromagnet. And so electromagnets use electric charge, or electric current more specifically, to create magnetic fields. And this is because moving charges create magnetic fields. So a wire with a current, which is just a fancy word for moving charge, creates a magnetic field. And the right-hand rule will tell you the direction. So for example, if I have a wire and I'm shooting charge through it, so a bunch of electrons are moving up through this wire, kind of in this vertical direction. That's going to create a magnetic field because the charges are moving. If you want to know why that happens, that's where, like I said, it's going to get into some stickier math and deeper concepts in physics, which if you're interested, I'm happy to talk through it. But if you're okay with just the overview of this is a thing that happens, we can stick with that for now. This will use a right-hand rule to tell you the direction. So the way this right-hand rule works, you take your thumb. So unlike before where you took your fingers, this one you take your thumb and you point it in the direction that the current's moving. So in this case, the current is moving up, and then you curl your fingers the way they'll naturally bend, and the magnetic field will wrap around the wire in that direction. So it will go all the way around the wire. So in this case, it will be kind of around in front and then back around behind like this. Around and back around like that. Does that make sense? If I had a wire coming out of the page or out of the screen like this, then from my perspective I see it like this, but for you, it's going to be like that. And I'm going to wrap my fingers around it. And when I do that, you'll notice I get it my fingers going in this direction. Let me draw them both in the same direction, yeah. So if there's a wire coming out of the screen, it's going to have magnetic field lines like that. If there's a wire going into the screen, it's going to have magnetic field lines in the opposite direction. Whoops, like that. So right-hand rule tells us the direction. Point your thumb in the direction of the current, and your fingers will wrap in the direction of the field. So then we can make this magnet, this will be a weak magnetic field and it's going to be wrapped around, which isn't particularly useful. But if that is wrapped into a coil, so I have a coil of wire like this, that's called a solenoid. And it will have a strong magnetic field through the center of the coil. So this will have a strong magnetic field pointed straight through the center here. And that's something that's easier to demonstrate and talk about and work through in person. So if you want to talk more about electromagnets or solenoids, ask me in class and I'll kind of go over it with you individually or in small groups. But the main thing here is knowing that if you have a current going through a wire, that's just a bunch of electrons moving, and that creates a magnetic field. Now, the opposite is where we're going to talk about how magnets create electric currents, or how magnets can create electric fields. So a magnet can produce a current. And this is known as electromagnetic induction. And a current is generated when a magnet is moved near a coil of wire. If it's not moved, then there's no current. So this is kind of like the opposite before, where if we move a bunch of electrons, that creates a magnetic field. So we're moving the electric thing to make the magnet thing. Now we're going to move the magnet thing to create the electric thing. So in both cases, if we have one moving, it creates the other. And this is where you can kind of see them being two sides of the same coin. It's not exactly this way, but you can think about like moving electricity makes magnets. Moving magnets makes electricity. Again, it's more nuanced than that, but that's how they're kind of connected here. So in order to get the real brief overview, we're going to talk about magnetic flux. And this gets very complicated, or not complicated, it gets very messy very quickly. So we're going to just do the skim over and just do the basic idea. Please ask questions if you want clarification, and we can kind of talk through some of the more details if you need them. The summary is that magnetic flux is a measure of how much magnetic field passes through a loop. So if I have a magnetic field like this, and I've got a loop of wire, there's a certain amount of field lines that pass through it. If I have my loop like this, then a different number of lines will go through the center of that wire. The amount, the measurement of that, which we're not going to worry about how we measure that, but that measurement is the flux. So when the magnetic flux changes, a current is induced in the loop. And there's two ways that we can change the amount of flux going through a loop. We can move, let me make sure I have the right phrase. Oh yeah, we can increase or decrease the strength of the magnetic field by moving the magnet closer or farther. So if you remember like a north-south magnet, at the poles, there's a lot more magnetic field lines closer than farther away. So if I move the loop closer or farther from the magnet, then the amount of lines going through that loop are going to change. You can also spin the loop or the field, which is changing the angle between the two. So that's where we saw this example here, right? If I have these lines, in the first example, there's 4 lines passing through. In the second example, no lines pass through that loop. So if I rotate or spin, and this is the one that tends to be more common for electromagnetic induction, is actually spinning a coil of wire or a loop of wire. But both will induce a current. So the main thing that I want to kind of summarize for you here is that electricity and magnetism are just two sides of the same coin. And kind of as a summary, if you have electricity, you can create magnetic fields. If you have magnetic fields, you can create electricity. And in both cases, it's done by essentially moving the magnet or moving the electricity to create the other field.